Okay, so this is, will there be a sign? Yes, I'm gonna make an assignment and post it, and I'll probably get it out later today. Seems to be, it'll be very short. It won't be due this weekend, it'll be due in the future, but it should provide some questions to help out. So yes, I didn't record at the start. So this is what we'll do on Tuesday, these 3 steps, and then we'll focus on things since the last midterm. So these are the main ones: alcohols, ethers. You'll notice on the practice midterm from last year, there was a section on conjugated dienes, which we haven't gotten to yet. So if you're looking at those questions, I wouldn't worry about it because we haven't done that yet. But this is what we'll basically focus on. But of course, we everything is basically built upon everything else. So it can't just be this stuff. There'll be other stuff included within it. The this is the code for the practice test: 9JHVK. Okay, so that's what's to start that, and I guess that's how the test will work. I'll have to give out a code in before it starts. So try this practice test and see if that works. I'll send an email out. Well, actually, everyone's probably in class, so but that's the code for that little practice test there. Now, so today's basic class was all going to be a review, so it's really whatever questions you have, we can go through. Right, so there's a question about, yes, if you want to send me a question to put on the test, if it's a good question, yeah, I would need it sooner rather than later. I would suggest by Sunday night at the very latest. And it can be on anything in anything really in organic chemistry. So it doesn't have to necessarily focus on the last stuff. If you've got a really super great question from earlier on in the term, that's fine too. And I can't guarantee it'll make it to the test, but we'll see. It might. Okay, so there's some questions about alcohols. Right. Okay, so let's do okay, so there's 2 questions on alcohols. One specifically about Williamson synthesis. So we'll do that one first. Why is my thing not working? Why did that work? Okay. Okay, Okay, maybe we'll go into the whiteboard then. I'm going to start a new share because stop it, go away. Yeah. Okay, it seems like, can you see this whiteboard here?
Yeah.
Okay, yeah, thanks thing. I don't know why the OneNote just suddenly decided to fail, but it did, at least with the pen. Okay, so Williamson synthesis. William. Okay, so this basically uses the sodium hydride and NaH. So put this in THF. Okay, so the hydride deprotonates your alcohol, and this gives you your anion plus H2 gas, which bubbles out. So the reason why sodium hydride is used is because it makes this step irreversible. Hydrogen bubbles out, and you formed what will become your nucleophile. And we want it to behave as a nucleophile and not as a base. And so the question was, can you only use it on primary or can you use it on secondary as well? So it's most often and reliably used on primary alkyl halides. So who knows this? Because when you use it on a primary alkyl halide, so this will be an SN2 reaction, you will form the product that you want. The amount of 1, 2, 3, 4. The amount of competing E2 elimination is lower. So in this case here, what the nucleophile I've got, this is a primary, we started out with a primary alcohol. You'll notice that with a lot of the examples that I do, I'll draw something slightly more complex, like say a cyclohexanol. And this is now this 1 carbon, 2 carbon, this is now a secondary alcohol. And the moment you start adding alkyl groups to the part which is going to become a nucleophile, so remember, we want this to be a nucleophile. But now it's becoming more and more bulky. And so if we try to do like a substitution reaction, say on a secondary alkyl, like on this, because we're starting to add sterics to what we want to be a nucleophile, it's going to become, instead of a nucleophile, a base. So typically, this works best with the primary alkyl halides or just a straight up methyl, like methyl iodide or methyl bromide. Remember our friend here, tert butoxide. Remember, this one was always a base because it had those 3 groups there and it was really bulky. So like with the complex molecules that we're dealing with, it becomes, when this becomes a secondary alcohol, or it's really becoming more and more bulky. So we have to limit the electrophiles to something which is not particularly sterically hindered. And this one, an SN2 reaction would be slow on it, where an E2 would be relatively fast. So we want to, so it's best with the primary or just methyl. So otherwise you're going to get some serious elimination byproducts, and that's not what we want. I suppose so typically that's how it would be. So I would avoid using it unless you've got a primary alcohol. Like that's the best way to do it with a primary alcohol. Does that make sense? So if you want to make something which is really, really crowded, the best way is the mercury diacetate and using an alkene of some variety. And so the nucleophile in this case is always going to add to the more substituted carbon. So you've got the options of making some pretty some ethers that have got a bit of steric bulk associated with them. Now the next question was basically a general overview of alcohols. So right. So what I would, as I sort of suggested last class, is that the best thing to do is to make a sort of a reaction web. And what I would do is I would make one for a primary alcohol, and I would make another one for a secondary alcohol. And I would even try to do one for a tertiary alcohol and see what reactions can take place with under all these various circumstances. So let's see. Now, we started off the section with oxidizing agents, right? So one type was with PCC, dichloromethane, and the other type was basically Jones. So Jones has got the water in it, right? Water and acetone. And for primary alcohols, this oxidation provides different products. So we've got our aldehyde, and in the fact for Jones, we've got the carboxylic acid. So when you do your reaction web with secondary or tertiary, with a tertiary alcohol, these reactions are going to be slightly different, right? But it's a good way of getting practice with each sort of one. So we did some oxidation reactions. Now, another thing we did was we converted these into alkyl halides of different flavors. So we had one with PBr3, which made a bromide. And we did one with thionyl chloride. And there's a whole bunch of electrons around here. And this made the chloride. Both of these reactions were SN2. So if you do a reaction web with tertiary alcohols, they're not going to be possible because you can't do an SN2 reaction on a tertiary alcohol. You can do an SN1 reaction. So you could conceivably put these things on, but you would be using HBr or HCl. That's how you basically have to do it. So you need to, so it's a completely different sort of pathway to get that to work. So, and yeah, so phosphorus tribromide, thionyl chloride, these will make the alkyl chlorides. We made leaving groups. We converted alcohols to leaving groups using something. We actually did this last term, but we had remember there's various R groups here, which would make the mesylate, the tosylate, the triflate, and we needed some sort of reagent to remove a proton, which could be triethylamine or pyridine, doesn't matter which one. And this would make the sulfonates, which are good leaving groups. So you could create, remember, they all varied by their R group. The mesylate was a methyl. The triflate was an aromatic ring. Sorry, the triflate was a methyl with 3 fluorines on it. The tosylate was the aromatic ring with the methyl on it. So the different varieties. So R equals Me. This would be the mesylate. R equals CF3. This would be the triflate. R equals this would be the tosylate. Tosylate's probably the most popular because that aromatic ring helps crystallize it to make it a solid, so it's a bit easier to work with. So this this makes a leaving group. So that's useful. That's because colors starting to drive me insane here. Let's do a different one. Then what else did we do? We could make ethers, right? NaH, Rx, what we just did. This is SN2. That's one way to make an ether. Second way to make an ether was with the mercury. And we would add that to the most substituted carbon. A, B, C, D. A, B, C. C, D. Now, what other reactions did we do with alcohols? Oh, we did. There's one other one I can think of, and that is the protecting group one. So we could convert that to a silyl ether using trimethyl silyl chloride and a base, and typically it's triethylamine or again the pyridine. Either one of those works. You'll notice that the two things that these two bases have in common is that the nitrogen's bonded it's got 3 bonds to carbon, so it really can't behave as a nucleophile in the way that it basically only can behave as a base, because so that was to make a protecting group. So this is basically a protected alcohol. So we've got one method to convert an alcohol into a protected alcohol. We've got one method to convert your alcohol into a really good leaving group, the sulfonates. We've got some functional group transformations converting the alcohol into either bromides or chlorides. And then we've got another functional group interconversion to make ethers with 2 different ways, depending upon if it's an SN2 reaction or if you're making a hindered ether. And then the ones we started off with at the start, where we are converting that alcohol functional group into carbonyl compounds, so aldehydes or carboxylic acids. And if you do the same sort of map with a secondary alcohol, the oxidation reactions are going to change ever so slightly. You can still do the protection, you can still do the converting it into a leaving group, these SN2 reactions would behave more slowly, and you could still do the Williamson synthesis on really simple alkyl halides, primary ones, and then this would still work too. But when you get into the tertiary, the oxidations aren't going to work at all because you can't oxidize tertiary alcohol. The SN2 reactions over here won't work at all. This Williamson synthesis reaction isn't going to work at all, with the exception of a methyl. Can't even work on a primary anymore because you've effectively got, if you can make a tertiary alcohol and you deprotect it, or sorry, deprotonate it, this is even worse than the tert butoxide, right? So this is only a base, This one's even worse because you've got a large ring associated with it as well. So there's a lot less reactions with the tertiary alcohols there. Okay. Now, the other thing with the alcohols is how to make them, right? So now the fun thing is that we've learned quite a few ways to do this. So if we have an alkene, we know how to make the most substituted alcohol. And we also know how to make the least substituted alcohol. DH3. Mercury. So we can make alcohols through alkenes. So that's one whole method there. Let's see here. We can even make designer like alcohols that are like diols. We know how to make the trans, and we know how to make the cis. So this was the osmium tetroxide route. This was the MCPBA, then either acid or base to make the trans. So with alkenes, you can make diols or the Markovnikov or anti-Markovnikov alcohol. So those were things that we'd done in the previous section of the course. The new way that we learned was basically through the various carbonyl compounds. And I'll put carboxylic acids here too. So we did, there's sort of a dividing line. It's sort of right here between these guys. So we've got aldehydes, ketones, ester, acid. So we could use reducing agents to create alcohols from here. So the reducing agents that we first talked about was sodium borohydride or lithium aluminum hydride. So So remember, the first step was the hydride itself. The second step in all of these reactions is going to be an acidic workup. So we stop the reaction by adding some sort of H, and that's going to protonate the alcohols. That's where this proton comes from. So with sodium borohydride or lithium aluminum hydride, aldehydes would be reduced to primary alcohols. Ketones would be reduced to secondary. So primary, secondary. Now with esters and carboxylic acids, sodium borohydride doesn't react with them. It's not strong enough. You'll find the odd example of sodium borohydride reducing an ester in the literature, but it's usually there's some sort of special circumstance which allows it to happen, and it's usually releasing some sort of ring strain or something like that. But in general, sodium borohydride with esters doesn't work. But lithium aluminum hydride does, and this will produce primary alcohols. Primary. So the general mechanism in each case is H minus attacks the carbonyl carbon, electrons move up, that gets protonated. With esters, it's basically a two-step process. So we'll do the ester mechanism. So aluminum minus H. I'll draw the H on here. Tetrahedral intermediate that isn't particularly stable, this decomposed, this we eject out the O minus. This is favored through entropy because you're making two molecules from one. So this is entropically favored. It's sure this oxygen could come back and attack, but eventually it's just going to get booted out. Then the hydride attacks a second time, and you end up with and then this gets protonated with the acid when you finally stop the reaction. So you basically end up with the primary alcohol. So with sodium borohydride's incapable of doing this, but lithium will reduce both of these in a similar fashion to primary alcohol. So that's the first thing we basically did. There is a similar analysis that we could do with Grignard reagents. So let's erase this. No, that's RMGX. XCl, sometimes iodide. Bromine's the most common one. So this is carbon with a minus, magnesium with a plus. So this is a source of R minus. Very basic and very nucleophilic. So if we have we draw all of our little guys out again. I'll draw the acid as well. You don't see that one as a common. You got to really react it quite strongly with that. Aldehyde, ketone, ester. Okay, now RMGX. And we'll just put excess here. So we're going to be using excess. If we want the reaction to go to completion, for the ester and the acid, you need excess. So anyway, so what we end up here with is that and then the second step is, of course, H3O plus. seconds. So aldehydes now become secondary alcohols. Ketones now become tertiary alcohols. Esters become tertiary alcohols. And so do acids. So both of these make the same thing. Tertiary. The difference here is that the tertiary ones for the esters, the R's added twice. And so whatever you started with, we'll call this, we'll make this a red R here. Red, red, red. The nucleophilic R, like with the ester, there's two of them. And with the ketone or the aldehyde, it's just added once. So the mechanism is exactly the same as the reduction mechanism that we drew up here. The only difference is rather than adding H minus, we're adding R minus. So this was these were the two new reactions that were sort of important for the synthesis of alcohol. So you could make an alcohol from carbonyl compounds. That was the key point. And I see it's already 10 o'clock. Oh my. Were there any other questions? I sort of didn't mean to take that long. Okay, if not, over the coming days, if you have any questions, fire me off an email. I'll try to put that assignment up sooner rather than later, like super soon. And that'll give you some practice. Look at the Moodle practice questions and the old midterm on which is posted on Moodle. Those will be helpful too. And if you come up with a question you think is wonderful, send it to me and I'll try to incorporate it into the test. And yeah. So, and make out little reaction webs for the various things that we've done. And you can start with really any molecule that you want. You can start out with this and do all of those same sort of things, or you can start out with who knows what, this. And it'll give you some practice and hopefully the realization that you can try it with basically anything you draw and get the various. Once you start doing the webs, then you're gonna get some realization of the various tools that you can use for these various sort of reactions. All of the quizzes should be open for review now. Today's one I will open up again, but they should be open on there for review right now. All right, so good luck, and yeah, send me an email if you have any questions. Okay.